Okay, so last time you did a lab over friction, and we really need to talk about what causes friction and some of the math behind it to really get you going there. So to start, we need to talk about what causes it. We had the wooden block and you had the table, and you were sliding it along with the hook here to see how much force it took to pull that block at a constant speed. If you were pulling at a constant speed, you were pulling with exactly the force of friction because there wasn't an acceleration there. So if we look at a little bit more microscopic level, on that table, there's some bumps and some ridges. It's not a perfectly smooth surface. And you also know that the block of wood or the brick that you were using has some bumps or ridges of its own, and that it's not a perfectly smooth surface. So friction is just those bumps or ridges either bumping over one another or scraping off and scraping through one another. You know this is true also when you rub your hands together. When you rub them together, you can feel yourself bumping over the knuckles, but you can also feel the skin kind of scraping over those ridges that are part of your fingerprints and your handprints. So if we look at what causes friction, it's just due to the irregularities in two surfaces. When they slide against each other, it either rises over or scrapes off those irregular bumps. And that force of friction between the surfaces depends on the kinds of material in contact and how much those surfaces are pressed together. The kinds of materials, that part is kind of obvious. If we have two hands that are put together, that's one thing. If we put lotion on our hands, it changes. If we put gloves on our hands, it changes. If you were dragging a piece of wood or if you were dragging a brick, there was a different amount of friction there. But it also matters how much those surfaces are pressed together. If you slide your hands across one another really lightly, there's a certain amount of friction. If you push really hard, there's a different amount of friction, and you can feel that. You can feel that your hands get hotter more quickly if you're pushing them together harder. And that is the only two things that friction depends on: the kinds of materials and how much those surfaces are pressed together. So a question here, and I wish I was here to ask you about this one, but I'm not. So which is more effective in stopping a car and why? You've got a metal guardrail here, or you've got these concrete barricades here. The metal guardrail is effective at stopping a car, but when it does that, it scrapes metal on metal right along about the door of the car, right where you would get in. This sort of a barricade, you'll notice that it is tapered out at the bottom. Well, the reason for that taper is so that the concrete hits the tire of your car. The tire has the most friction of any surface on your car. That's why it's in contact with the road. And this is actually a lot more effective in stopping a car quickly because that tire rubs along this concrete barricade and slows your car down more effectively and also causes less damage than a metal guardrail. This is a friction application. We're looking at two surfaces that can be pressed together to quickly stop your car. And so this is your best option if you want to stop the car quickly. Now, why don't we use these everywhere? Well, there's places where they don't fit. There's places where the weight is inefficient, or there's places where this is just a lot cheaper and we just need to make sure that your car doesn't fall in the river because that would be bad. There's four types of friction, and we'll look at each of them just real briefly here. The first is static friction. Static typically means staying still or not moving. That's the force of friction that keeps an object from moving. So if you're moving a refrigerator, you've probably noticed that it takes a certain amount of force just to get that refrigerator moving. Football boys, if you think about pushing the 5-man sled, it takes quite a bit of force to get that sled started. That's overcoming the force of static friction. The next one is sliding friction, and I'll go back to the sled example. It takes a lot of force to get it started moving. It takes a little bit less force to keep it moving or to keep it sliding. Sliding friction is the force of friction on objects that are already moving, and it is almost always lower than static friction. So this sliding friction is less than static friction. It takes a certain amount of force to start it moving, and then it takes a little bit less force to keep it moving. Rolling friction is another type of friction. This is friction on a rolling object such as a ball or a wheel. Ball bearings would be a good example of this. Roller skates, roller blades, any sort of thing that is rolling along would exhibit rolling friction. And this is again, almost always less than sliding friction. We know that things that roll typically have less friction than things that are sliding. And then finally, fluid friction is the last type. This occurs as objects push aside fluids as they move through them. Air resistance would fall into this category, but so would water resistance. As you've been swimming, you can feel that water is pushing against you, and you have to continue to propel yourself forward in order to keep going. Inertia doesn't allow you to just keep going because fluid friction is pushing back against you. Now we can calculate friction, and that's actually pretty helpful, and it's used probably more than you think it is. For every surface or set of surfaces, there's a coefficient of friction that helps us to calculate the force of friction from those objects. The symbol for this is kind of this funky looking U, and it's pronounced mu. That is the symbol for the coefficient of friction. My wife and I are actually remodeling a part of our house, and we were looking at tile the other day, and one of the things on the tile packages was the coefficient of friction, or the mu, for those different types of tile. So it said mu 0.7. That was the coefficient of friction that we were given for that type of tile. So this is something that's used even beyond a science classroom. There's some relevance there. The equation that we use for this is the force of friction equals mu, or that coefficient, and it's just a number, almost always less than 1, times the normal force, which for our purposes is equal to the force of gravity. Or you could also say that it's equal to the weight of an object. Force of gravity and weight really are the same thing, and we'll do everything on flat surfaces for right now. So the force of friction is equal to mu, or that coefficient, times the force of gravity, or the weight of an object. So a couple questions here are examples of how we do this. Unbeknownst to students, every time the cafeteria floors are waxed, Mr. Baumgartner likes to slide across the floor in his socks. Just close your eyes and imagine that for a second. Mr. Baumgartner weighs 850 newtons, and the coefficient of sliding friction between his socks and the freshly waxed floor is 0.120. What is the force of friction that opposes Mr. Baumgartner's motion down the hall? Well, we're looking for the force of friction. We know that mu is 0.12, and we know that the normal force, or the weight of Mr. Baumgartner, is 850 newtons. All we have to do here is multiply. So these problems are actually quite simple. All we would do is take 0.12 times 850, and we should get 102 newtons of friction. And that's what we get. Sorry, I wrote over the answer there. But there would be 102 newtons of friction in this question. Another question for you is, Casey's taking a shower, the soap falls out of the soap dish, and he steps on it with a force of 500 newtons. If Casey slides forward and the frictional force between the soap and the tub is 50 newtons, what is the coefficient of friction between these two surfaces? Well, here we know the force of friction is 50 newtons. We're looking for the coefficient, or mu, and we know that the normal force, or the weight of Casey, was 500 newtons. All we have to do here is divide to find mu, so we'll divide by 500. Sorry, I shouldn't have had that dot there. And we'll get 0.10 equals mu. We'll skip this one because we don't really need it. Okay, now we're back where we need to be. So I want you to try this with a partner, or maybe in a group of 3 or 4. I want you to grab some spring scales and connect the hooks of the 2 spring balances and play tug of war. Those spring scales are those tube-looking things with the handles on them, and then they've got a hook on one end. And I just want you to hook 2 of those together and play tug of war. Please don't break the spring scales. Just connect them together, pull a little bit, and I want you to try to have one person pull harder than the other and read the scales. So try to have one person exert more force than the other force, again, without breaking the scales, please. Go ahead and pause the video so that you can do this. You should have noticed that the readings on the scales stay the same. No matter how hard one person pulls, the other person has to pull back just as hard. And that's the third law of motion. There's no way for one person to exert a force without causing the other person to interact. Another way that you could do this would be to give a high five. If one of you tries to give a high five harder than the other person hits you back, you'll notice that both of your hands sting. If you're an intense athlete and you give super hard high fives sometimes, you'll notice that your hand hurts also. Both people's hands sting because both people exerted a force on the other person's hand. So we sometimes will say that forces only occur in pairs because there has to be an equal and opposite reaction force for every force. And that's Newton's third law. Whenever one object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. One force is called the action force. That's typically the first one named. The other force is called the reaction force. It really doesn't matter which is which, but they are always present. Sometimes we state this that for every action there's an equal and opposite reaction. That is not really true. For every action force, there's an equal and opposite reaction force. It has more to do with just action-reaction. It has everything to do with forces that are on these objects. So let's find the action and reaction forces in the following systems. In a car, and you can see the arrows here, the tires actually push the earth backwards. It's a little bit hard to think about, but if you think about how your tires turn, they turn this direction, and they're pushing the earth backwards like that. The earth then pushes the car forward. That's a little bit counterintuitive, but the car is not pushing forward. In fact, when the car pushes forward, it drives in reverse. The car pushes backwards and the earth pushes the car forward. In a jet plane or a rocket, well, the rocket pushes air backwards and the air then propels the rocket forwards. The rocket is obviously much bigger, so it takes a lot of air moving at a high speed to get a rocket to propel. But that's how a rocket propels itself forward. It pushes air back and the air pushes it forwards. With a ball dropped from a tower, well, the earth pulls the ball down and the ball actually pulls the earth up. Now the earth is huge, so it doesn't move very much. In fact, it really doesn't move at all. But the ball is exerting a force on the earth just like the earth exerts a force on the ball. A couple more examples. A person's hand hitting a wall. Well, the wall exerts a force that is equal and opposite back on the hand, and that's why your hand hurts if you punch a wall. That's not recommended, kids. With pool balls, ball A hits ball B. Well, ball B gets propelled forward, and sometimes we would say, well, that's the reaction force. That's not the reaction force. That is what happens, but that's not a reaction force. Ball A hits ball B hits ball A. Equal and opposite, and ball A stops. There has to be a force on ball A in order to get it to stop. When you walk, you push the earth backwards, and the earth propels you forwards. And then again with the rocket ship, it propels air back, and the air propels the rocket forward. This one is a little bit more challenging, and we could look at the action and reaction pairs here. The cannon propels the cannonball forward, so it pushes the ball forward. The ball pushes the cannon back. I want you to talk just briefly with your partner about why the cannon moves less. Once you talk with that, you can go ahead and do the homework that I've assigned you in the email, and have a good day.